So we'll talk about our project. We'll share our results of HydrAMP. We are working on a HydrAMP project, and our work was mostly concentrated on iterative latent space optimization, hence the ILSO abbreviation. So we would like to begin with the motivation. What do we need HydrAMP for? So it's not yet our work, it's what was before we started with the project. So basically, the most common cause for deaths is the antimicrobial resistance of human, where they don't react, like we don't have a good treatment for that. Hence, the solution would be to create peptides that would be able to destroy those microbes. But the issue is that many of the peptides are either insufficient, whereas they don't do harm to our viruses, or they are toxic to people, where what we actually don't want, we don't want to kill people that we treat. Hence, we want to find some peptides that will actually work. And basically, current approach is we just get something that we know it works okay, and we find in a neighborhood similar peptides, and that is the solution, but it's all done by hand. Hence, the HydrAMP solves it by generating it using machine learning. And so far, before our work, they were able to generate 15 or 25, depending on the criterion, peptides. And some of them are patented by the team working in our faculty. And now we'll talk more about our work for the project. But first, we'll start with describing a modified model for generating, defining the model for HydrAMP, the original one, and our modified model for generating the peptides.
Okay, so this is an architecture which was before we started. As you can see, it's kind of complex, and it's hard to find out what is going on. But for now, I will focus on one thing. Like here we've got encoder, which creates vector peptide representation in latent. As you can see, this is representation from encoder, and there are two more places, which means what is AMP score and MIC score. So encoder creates just this representation above it, and then we add these two numbers to our representation, and this is the latent vector in latent, which comes into decoder. So what we have done is we slightly changed it. Now encoder gives us entire representation of peptide, and AMP and MIC score comes from some operations on this vector, which gives us opportunity to slightly change sampling process. Change things. Okay, so now we count AMP by calculating dot product of normalized normalized vector representation and normalized weights, and that's it. And second one, MIC, is just a length of this vector which represents peptide, which is very simple now, and it is easy. We can easily calculate it and change it. Okay, this is an image of latent space based on two first principal components. As you can see, this latent has a lot of orange to the right and a lot of blue to the left, and there is this red dot which is a direction of this AMP. As you can see, orange, which are peptides with high AMP probability, are to the right, as well as this red dot from the 0 point. So we managed to create a reasonable latent space which divides these negative samples from positives. Sorry, it's my slide. I forgot. And now sampling process is much easier than before because we can just calculate gradients using these AMP and MIC values from vector representation, and just slightly change this vector into this direction which we want. We can also do one more thing. We can change length of this vector to change MIC. And so this sampling is very easy. We choose base peptides, encode it, calculate AMP from encoded representation, perform gradient descents to maximize AMP prediction, decode new representation, and get new peptide. We repeat 4 and 5 as many times as we want to create many samples.
Okay, so I'll now talk about iterative retraining of our model. And the idea is that we have a pre-trained model that are able to predict the MIC and AMP values, which are whether or not it is able to kill those microbes, and whether or not they are toxic. So these are these two values. And the main idea for our retraining is that if we have our training set, then the model is able to actually generate something from our dashed line field, and this is what it's able to generate from the samples, which are these color dots. So we see that only one sample falls into our reward territory, where actually we get the good value of MIC and AMP. So there is not much room for generating new peptides, and the idea is that if we know that that there are peptides which are good based on our predictions of AMP and MIC value, we can just add it to our data set, so that now our model might use the not perfect data points, just some of its imagination of what the data looks like, but it will be focused more on that reward space, and hence reach the better results. And spoiler alert, it actually happens in our case. We do get better results, but let's not get too ahead of time. So how do we exactly get it? So basically, in each we have different times at which we add a new samples to our data set. I will explain it later, but basically we used weights for our samples. Because we don't want to get poor data and actually have it significantly impact our training process. Hence we use the formula as given, where rank is just how many better examples there are. So we see that the lower the rank, the better the examples are, the higher weight they get assigned. And in our training, we used this factor to be equal to 1. So the best example is 1 over n, has weight 1 over n, just to put it somewhere, not to divide by 0, but that's an implementation thing. And basically, we have 3 or 4, depending on how we count, because we have either basic models where we don't add examples. Then we have a model where we add examples after each epoch. Then we have a model where after after training to a certain point, we add new examples and then restart the whole training process. We restart weights. And then we have a model where we train to a certain point, the standard way, and then for a few epochs, we just add examples. And here are the results. So on the left side, we see the results generated throughout the whole, all the results generated by the models throughout the training process. And we see that HydrAMP works, like has a high risk, high reward, much higher than the standard HydrAMP. But focusing only on the HydrAMP, we see that actually adding the iterative latent space optimization, we see a wider top part, hence the generated examples are much better qualitatively. And here on the right side, yeah, we see top 6 generated peptides. And basically, those asterisks means that we perform the Mann-Whitney test on them, comparing to the pure HydrAMP. And the one asterisk means that they are better with a p-value of 0.1, and double asterisk with 0.01, if I'm correct. And basically, also, why we had to compare top 6 is just because the HydrAMP model has struggles with creating a lot of examples, but that's a problem which other team that will present just after us will face, were facing, and had a solution for that. All right.
Okay.
Thank you.
Let's thank the